Hi, I am Marnil Anap, and in this video we will try to solve problems involving center of gravity, parallel axis theorem, composite area, product of inertia, and mass moment of inertia. So, let's get started. For our first problem, locate the centroid x bar, y bar of the shaded area in the figure. In the figure, we have the value of y, which is 1/6 x cubed. In order to find a centroid of a curve, we are going to use the formula x bar is equal to the integral of x curly dA over the integral of dA. The same formula for y bar, but we are going to change the variable x to y. From the formula, we are going to identify the value of dA, the x curly, and the y curly. In order to find dA, let us consider a rectangular element parallel to y-axis. It has a thickness of dx and a height of y. So, the value of dA is dx times y. The x curly and y curly are the centroid of the rectangular elements. So, the value of x curly is equal to x, and the value for y curly is equal to the half of y. Now that we already have all the values that we need, let us apply it to the formula. For the x bar, let us substitute the value of x curly, which is equal to x, and dA, which is equal to y dx. Performing further integration, we can get that the value of our x bar is 2.4. Let's proceed to y bar. Let us substitute the value for y curly, which is equal to y over 2, and dA is y dx. Then, substitute for the value of y, which is equal to 1 over 6 x cubed. By further integration, we can get that the value of our y bar is equal to 1.9. So, the shaded area has a centroid of 2.4 and 1.9. This time, let's try to understand some basic concepts of parallel axis theorem by solving our next problem. In this problem, we are going to determine the moment of inertia along x-axis. The first thing that I want to do here is to divide the figure into 3 sections. The parallel axis theorem states that the moment of inertia along x is equal to the ix prime plus ad with respect to y squared. Since our figure has a rectangular section, the value for ix prime is equals to 112 base times height cubed. Note that this equation is only applicable for rectangular shapes. Let us proceed on solving the moment of inertia of each section. As we can see, the section 1 and 2 are symmetrical, so they have the same value of moment of inertia. Let us solve for centroidal moment of the section 1 and 2. Ix prime is equals to 1 over 12 times 1 times 3 cubed, which is equal to 2.25. By adding it with the value of ad squared, we can get that the moment of inertia of the section 1 and 2 is 14.25 meters raised to 4. Let us proceed to section 3. The ix prime is equal to 1 over 12 times 6 times 1 raised to 3, which is equal to 0.5. However, in this section, we don't have to find the ad squared since it was already on the centroid. So the value for the moment of the third section is equal to 0.5 meter to the fourth. To find the moment of inertia of the figure, let us twice the value of our moment of inertia for the section 1 and 2 plus the moment of inertia for the section 3, which is 2 times 14.25 plus 0.5 is equal to 29 as our final answer. This time, let's try solving problems involving composite areas. Determine the moment of inertia of the shaded area about the x-axis. In this problem, we can divide the figure into 3 segments, 2 triangle and 1 square. We can identify the moment of inertia of each of the segments using the parallel axis theorem. We are going to use tables in solving the problems in order to make it simple. For our second column, we are going to identify the area of each of the segment. For our square, the area is equal to 4 times 4. And for our triangle is 1/2 base times height. For our second segment, 1/2 times 2 times 4 is the area. And for our third segment, it has 1/2 times 4 times 6. Let's proceed to our third column. In the third column, we are going to determine the distance of each of the centroid of the segments from the x-axis. So for our square, the centroid is at the center of the square and it has a distance from x which is equal to 2. For our second segment, it has a centroid of 1/3 of its height plus 4 in order for it to reach the x-axis. For our third segment, the centroid is at a 2/3 of the height, which is a 2/3 of 6 is 4. For our fourth column, we are going to determine the moment of inertia of the centroid of each of the segments. For our square, we are going to use 1/12 base times height cube, and for our triangle is 1/36 base times height cube. Let's move on to our fifth column, which is we are going to determine the AD squared with respect to y. We can get it by squaring our third column and add it with our second column. So for our square, it has 64. For our second segment, it has 87.24. And for the third segment, it has 192. For our last column, we are going to determine the moment of inertia of each of the segments. We can get it by adding the results of our fourth column and our fifth column. So, for our first segment, it has 85.33. For the second segment, it has 88.13. And for the third segment, it has 2.216. Now, let us proceed on determining the moment of inertia of our figure. We can identify it by adding all the moment of inertia of all the sections. So, 85.33 plus 88.13 plus 216, the moment of inertia of the figure is equal to 369.46 inches to the fourth. Our next problem is about the product of inertia. Determine the product of the moment of inertia of the shaded area with respect to x and y axis. As we can observe, this problem is exactly the same as what we have in our first problem, but this time we are going to identify for the product moment of inertia. The area for the differential element parallel to y-axis which is dA is equals to y dx. Same as what we have in our first problem, x curly is equals to x and y curly is equals to y over 2. The product of inertia of this element with respect to x and y axis can be determined also using the parallel axis theorem. The differential moment of inertia with respect to x and y is equal to di with respect to x and y prime plus the dA x curly and y curly. From that, the dI with respect to x and y prime is equal to 0 due to symmetry. So, the dI with respect to x and y is equals to 0 plus the dA x curly and y curly. So let us substitute the value of dA, which is equals to y dx, and the value of x curly, which is x, and the value for y curly is y over 2. Next is substitute the value of y, which is 1/6 x cubed. From that, we can get 1 over 6 x cubed dx times x times 1/2 times 1/6 x cubed, which is equal to 1 over 72 x to the 7 dx. By integrating with respect to x from 0 to 3, we can get the integral of 1 over 72 x to the 7th dx from 0 to 3. By performing further integration, we can get that the value of the product of inertia is equal to 11.39 inches to the 4th. For our last problem, let us solve for the mass moment of inertia. If the plate shown in the figure has a density of 5,000 kg meter cube and has a thickness of 2 mm, determine its mass moment of inertia about an axis perpendicular to the page and passing through the pin at point O. The plate consists of two composite parts, the 0.3 meter radius disc and the 0.15 radius, which is considered as the whole. The moment of inertia about O of these parts can be determined by finding the moment of inertia of each of these parts about O and then algebraically adding them. Let us solve this problem using the parallel axis theorem in conjunction with the mass moment of inertia formula for circular disc, which is I is equals to 1/2 mr squared. Let us start with solving the bigger disc with the 0.3 meter radius. First, let's find the mass of the bigger disc by multiplying the density and its volume. The density is equals to 5,000 kg meter cube times the volume, which is pi r squared times height, so it's pi times 0.3 meter squared times the height of 0.02. So the mass of the bigger disc is equal to 28.27 kilograms. Let us proceed on solving the mass moment of the inertia of the bigger disc, which is equal to Ig plus md squared, where Ig is equals to 1/2 mr squared. Let us substitute the value for the mass, for the radius, and for the displacement. So we will have 1/2 times 28.27 kilograms times 0.3 meter squared, 0.3 meter squared, plus 28.27 kilograms times 0.3 meter squared. So we got 3.82 kilogram meter squared. Let us proceed on finding the moment of inertia or the mass moment of inertia for our hole. Let us start with determining the mass of the smaller hole. In order to find the mass, we are going to multiply the density and its volume. The density is equals to 5,000 kg meter cube and the volume is equals to pi times 0.15 squared times 0.2 meter. So we have the mass of 7.07 kilograms. Now, let us solve the mass moment of inertia for the smaller hole by using the formula and substituting the values. Our mass is equal to 7.07, our radius is 0.15, and a displacement of 0.3. 1/2 of the mass times the squared of the radius plus the mass times the displacement squared. Mass moment of inertia for the smaller this is equal to 0.7158 kilogram meter squared. To finally get the mass moment of inertia for the plate, we are going to subtract the mass moment of inertia of our smaller disc to the bigger disc, which is 3.82 minus 0.7158. We will have 3.10 kilogram meter squared as the final answer. And that's all for this video, and thank you for watching.